My application question is about phase changes and the difference between them. My application question states, refer to figure 5.8. Explain the significance of the difference in the region between B and C compared with that between D and E. Use diagrams to support your explanation. In figure 5.8, the illustration below is the heating curve for water, which represents what water molecules as they enter the phase change. The tightly packed particles represents the solid state, and the liquid particles have space to move around, increasing energy. Lastly, the gaseous particles can move with greater kinetic energy because they have more space to move. As you can see from figure 5.8, between the points of B and C, the solid ice is melting to form liquid water. Between the points of D and E, the liquid water is boiling to form water vapor. Phase change is a change from one state of matter, either a solid, liquid, or gas, to another. Phase changes are physical changes because it only affects the physical appearance, not the chemical makeup. A phase change can be reversible. Figure 1 shows the states of matter and the processes they undergo in order to proceed from one state onto another. During a phase change, heat energy is either absorbed or released. Heat energy is released as molecules slow down and move closer together, while heat energy is absorbed as molecules speed up and expand. Endothermic energy is when the intermolecular bonds break. In this case, the hydrogen bonds between the water molecule energy is absorbed to change the state of energy, while exothermic energy is when heat is released and bonds form. In figure 2, the green arrows show the exothermic release of energy, while the red arrows depicted in this diagram represents the endothermic energy absorbed when the hydrogen bonds in water break. Melting is the phase change from a solid to a liquid. As you can see in figure 3, the solid ice is melting into the liquid water. This happens because while the heat is being absorbed, the hydrogen bonds are also weakening. The melting temperature doesn't change due to the heat of fusion. Immediately after the molecular bonds in the ice are broken, the molecules are moving or vibrating at the same average speed as before, so their average kinetic energy remains the same. Boiling is a phase change from a liquid to gas which occurs at the boiling point of matter. The heat absorbed is used to break the hydrogen bonds. The boiling temperature doesn't change due to the heat of vaporization. When energy is added to a liquid at the boiling temperature, it converts the liquid into a gas at the same temperature. In this case, the energy added to the liquid goes into breaking the bonds between the liquid molecules without causing temperature to change. In figure 6, this animation shows how water molecules are able to break the forces of attraction, the hydrogen bonds, and escape as the gas molecule. This is what's happening inside the gas bubble, as it is rising to the surface to break and release the water gas molecules. The melting and boiling phase are similar because they both absorb heat, making them endothermic. As shown in figure 2, the red arrows in the left of the diagram depict that they are both going in the same direction. Molecules speed up and move farther apart, causing an absorption of heat while keeping a constant temperature. As mentioned before, the clear differences between the melting and boiling phase is that the process of melting ice into liquid requires heat of fusion, while the boiling phase requires heat of vaporization. In the boiling phase, water bubbles form as seen in figure 5. Water molecules are able to break the hydrogen bonds and escape as gas molecules.
I'm wearing a hot pink shirt because we're going to talk about heat in this lesson. Specifically, we're going to talk about how heat moves during phase changes. And we're going to learn which phase changes are exothermic and which phase changes are endothermic. So in this diagram here, I have some phase changes that are very familiar to you from daily life. I have some solid ice, a big hunk of solid ice, melting to become liquid water. And then I have this liquid water boiling to become steam, which is a gas. So are these phase changes endothermic or exothermic? Let's think about what we have to do with heat to make them happen. So I have my chunk of solid ice. I've got to make it hotter in order to get liquid water. And then when I get liquid water, I've got to make that hotter and hotter and hotter in order to end up with steam. Now, when we want to figure out whether something is exothermic or endothermic, sometimes it's not as useful to think about whether we need to make it hotter or whether we need to make something colder. Instead, it's best to think about the direction that heat is moving. Let me show you what I mean. Let's use this red arrow here to show the direction that heat moves. Okay? So here I have this solid ice, and when I want to turn it into water, I've got to put heat into it. Okay? So here these arrows show heat going in. Maybe this heat is from a stove, maybe the heat is from the sun, maybe the heat's from a fire or something like that, but whatever the source, the heat is moving into the solid ice and melting it. And then once I have liquid water, I have to put heat into that in order to get steam. Again, maybe the heat's coming from the sun or the stove or something like that, but it's moving in. So we can say that heat is moving from the environment into the ice, heat is moving from the environment into the water. So heat moves from environment into water here. Or if we wanted to sound more scientific about it, we'd say that heat, in this case, moves from the surroundings, a fancy word for the environment, into the system. The system is just whatever we want to focus on. Here the system is the ice. Here the system is the liquid water. But in all of these cases, when heat is moving from the surroundings into a system, we are talking about an endothermic process. You can remember this because N sounds kind of like in, and that's just what's happening. Heat is moving into the system, it's moving into the water, it's moving into the ice. Endothermic. Now sometimes people get confused and they think, wait, I thought an endothermic process was one that felt cold. And here we're talking about having to make stuff hotter, and somehow that's an endothermic process. Well, sometimes things that are endothermic feel cold, but sometimes they don't. And instead of thinking about whether something feels cold or whether it feels hot, it's best to always think about the direction that heat moves, and you'll never get this wrong. And if heat is moving from the outside into something, it is an example of an endothermic process. Let's look at some exothermic processes. Okay, so what I have here is some steam condensing to form liquid water. You may not be familiar with that word, but it's just what we call it when steam becomes water, condensing. And now liquid water is freezing to make solid ice. To do each one of these phase changes, we have to make it colder. But instead of thinking about having to make something hotter or something colder, let's think about the direction. Here's my paper. Let's think about the direction that heat moves. Okay? If we want to go from this really hot gas to this cooler liquid water, we're going to want to move heat out of the steam. Okay? And here are the red arrows showing the movement of that heat. Maybe the heat is leaving the steam and going into a freezer or refrigerator or something. And similarly, to go from liquid water and freeze it to make solid ice, we have to get heat out of it to cool it down. So the heat is moving away from the liquid water. In this case, we're talking about an example where heat moves out of a system into the surroundings. And when heat moves out of the steam or of the liquid water, we call this an exothermic process. X meaning out of, and that's the direction of heat movement in these processes. Okay, so just to review, in melting and boiling, we have to put heat into the system, and that means that it's an endothermic process. On the other hand, for condensing, which is gas to liquid, or freezing, liquid to solid, the heat has to come out of the system into the surroundings. To cool it down, we have to pull that heat out, and that is an example of an exothermic process. Now, in the examples that I did previously, I was talking about water, okay? But this is no different with any other substance, whether it's ethanol or methane or anything you can think of. Melting and boiling, we have to put heat in, they're endothermic. Condensing and freezing, we have to take heat out, it's exothermic. Water, anything else, it doesn't matter. So don't think that it's just water. Now finally, we can describe these endothermic and exothermic phase changes using some numbers. As we've said previously, an endothermic process is one where the change in enthalpy, the delta H, is a positive number. And the exothermic processes are ones where the delta H is a negative number. Okay, so check this out. Here is the chemical equation for melting. I'm going from solid H2O to liquid H2O, and the delta H for the reaction, a positive number. Check that out, so it has to be endothermic. And the same thing for boiling, which is liquid H2O to gas H2O, liquid to steam. The delta H is a positive number again, so it's an endothermic process. Condensing, going from gas to liquid, is a negative delta H, so it's exothermic, and similarly freezing, going from liquid to solid, is a negative delta H as well. So that is how you can tell whether a phase change is an endothermic or an exothermic process. If you're putting heat in from surrounding to system, it's endothermic. If heat is going from system out into the surroundings to cool something down, it is an exothermic process.